Every time you open Uber and it tells you your driver arrives in 4 minutes, there's a massive AI system working behind the scenes to make that number true. And Uber just rebuilt that entire system from scratch. The result? $100 million a year in extra revenue, better route, and one of the biggest AI models on the planet, quietly running 2 million predictions every single second. Let's break down how it works. Here's something most people never think about. When you request a ride, the app instantly does two things. It picks a route and it estimates your arrival time. Both of those depend on one thing: knowing how fast traffic is moving on every single road right now and in the near future. Uber calls this traffic forecasting, and it's been running for over a decade. It works like this. Driver phones send a GPS ping roughly every 4 seconds. Multiply that across millions of trips, and Uber gets tens of billions of location pings a day. Those get mapped onto a global road network of about 100 million road segments. Think of it as a giant digital map broken into tiny puzzle pieces, where each piece is a stretch of road. From that data, Uber predicts how long it'll take to drive across each little piece of road, not just right now, but hours into the future. Add up the pieces along your route, and you get your estimated arrival time. The old system did this using a fairly simple statistical blend of recent data plus historical patterns. It worked well, but Uber wanted to push it further, especially in 3 tricky situations: sudden traffic incidents, quiet rural roads with little data, and long trips where small errors stack up. That's where deep learning, AI, comes in. Before writing a single line of AI code, Uber's engineers made 2 decisions that most people would never think about, but that made or broke the entire project. Decision 1. Should the AI model try to control the whole system end-to-end, traffic prediction and route picking, all trained together? Sounds elegant in theory. In practice, Uber said no. Their existing routing engine already works great, and it would have been way too risky to rebuild it. So they drew a clean line. The AI's only job is to predict how long it takes to cross each road segment. The routing engine, a separate, already proven system, takes those predictions and picks the best path. Think of it like an engine and a GPS. You don't need to rebuild the GPS just because you got a better engine. Decision 2 is more technical, but just as important. AI models that process raw, real-time data streams, the fancy graph-based models researchers love, need to load huge, constantly changing chunks of data. At Uber's scale, that's a nightmare for speed and memory. So instead, they pre-processed and compressed the data into a fixed, predictable shape before feeding it to the model. Slightly less theoretically powerful, but dramatically faster and more reliable at scale. And at 2 million predictions per second, reliable wins every time. Before building the model, Uber's team wrote down exactly what it needed to promise, like a contract. Promise number 1. Every 5 minutes, predict how long it takes to cross each road segment for up to 3 hours into the future. Promise number 2. When you add up all those segment predictions along a full route, the total trip estimate should be more accurate than the old system. Here's the twist. These 2 goals don't automatically go together. You can make every tiny segment prediction slightly better and somehow make the full trip prediction worse. That sounds like a paradox, and Uber's engineers had to figure out why. This is honestly the smartest part of the whole story, and it applies way beyond traffic apps. Uber's engineers split prediction accuracy into 2 separate ingredients. Resolution, how much real information the model is capturing. Basically, is it actually picking up on real patterns in the world? Calibration, whether the model's numbers are systematically too high or too low, like a scale that's always off by 2 pounds. Here's the key insight. Resolution is hard to improve. That takes genuinely better AI. But calibration is easy to fix. You can basically just recalibrate the numbers after the fact, the same way you'd zero out a bathroom scale. So Uber's strategy became, let the AI focus entirely on squeezing out more real information, more resolution, and treat calibration as a separate, solvable problem. That single insight is why, when they measured it, tiny millisecond level improvements at the road segment level snowballed into meaningfully better predictions for entire trips. So what is this AI model actually doing? It's called DeepETT, and it's built on a transformer, the same family of AI architecture behind tools like ChatGPT, just applied to traffic instead of language. Here's the clever part. Instead of only looking at one road segment in isolation, the model looks at multiple views of the same spot at once. Recent activity in the last hour, what usually happens at this time of day, patterns over the past few weeks, nearby roads, the wider neighborhood, holidays, and events. Each of these becomes a little data token, similar to how ChatGPT treats each word as a token, and the transformer learns which of these views to trust most in any given situation. Busy downtown street with tons of recent data? Lean on real-time info? Quiet back road with barely any traffic data? Lean on the surrounding neighborhood instead. The model automatically learns to shift its attention depending on the situation, without ever changing its basic shape, which is what keeps it fast enough to run at massive scale. Here's where things got got interesting. When Uber rolled out the smarter AI model, arrival time accuracy actually got worse at first. Not better, worse. The culprit wasn't the AI itself, it was calibration drift. Every week, when the model retrained, its numbers would start out well calibrated, and then slowly drift off over the following days in different directions depending on the city and time of day. Tiny miscalibrations at the road level snowballed into big errors by the time you added up a whole trip. Their fix: a real-time correction system that continuously compares predictions against what's actually happening on the road and nudges the numbers back into line, constantly, automatically, city by city. Once that was in place, the calibration curve stayed flat and stable, even during chaotic events like New Year's Eve in New York City. So what did all this engineering actually deliver? Long trip arrival time accuracy improved by 6%. The model captures 19% more real traffic information than before. Navigation errors dropped by nearly 3%, and overall, it's driving an estimated $100 million in extra revenue every year. There was even a real example from São Paulo: 2 identical trips leaving the airport at the same time. With the old system, the route missed a slowdown near downtown and arrived over a minute off. With the new AI-powered system, it rerouted around the slowdown and landed within 2 seconds of the predicted arrival time. The bigger lesson here isn't really about traffic, it's about how to build and ship AI responsibly at massive scale. Define clear contracts up front. Separate is the model learning real patterns from are the numbers systematically off, and never assume a model that works great on day one will stay that way without constant monitoring. Next time your Uber ETA is scarily accurate, you'll know there's a transformer model, 2 million predictions per second, and a whole lot of careful engineering behind that number. If you found this breakdown useful, subscribe. We break down real engineering blogs from companies like Uber, Netflix, and Google every week.